Okay, so next section we need to talk about this 4.3 concavity and points of inflection. So let me quickly explain what concavity is, just kind of to give you an intuition, right? So basically, right, so if you have a curve, then this shape, right, is a concave, we'll be talking about concavity of this curve, right? So in this, we'll be we'll be talking about two cases, two options, right? Concavity down and concavity up, right? So each curve can have either of those. And then, so that's concavity, basically shape of the curve, right? How the curve bends. And the second part here is inflection points, right? Or points of inflection. And what that means is that, let's say we have, right? So this is concave up, and then we have concave down, right? So the point where the curve switches between concave down or concave up to the other one, that will be those points of inflection. Okay, so let's start with an example. Right, so something simple. We'll look at y equals x squared. So consider f of x equals x squared, and yeah, we won't really be calculating. So the point of this section of this lesson is to be able to figure out what the concavity is without seeing the graph, right? Without being able to just kind of figure it out analytically. Okay, so when you look at this, right, y equals x squared, you see that, right? So this is, we have the concave is up, right? Is opening up. So let's write it, concave up. And yeah, let's look at a couple things. So first thing is that when you look at right, we'll look at the graph from left to right. So just kind of walking this way or looking at it this way. So you see that if I start graphing those tangent lines, right? So let's make one maybe here. Okay, so it'd be tangent line or line tangent to the graph at that point. And then we could move maybe here. All right, so the graph, I mean, the slope of that first tangent line, I don't know what this could be, right? And could be maybe -4. Then the second line, m equals -1. All right, so the slopes are increasing. All right, so that's it's one thing. It's a good thing to notice that. One thing that's important. So here the slope will be 0, right? And then if we move to the positive side of the x-axis, and you'll see that the slopes will be positive now. So this could be m equals maybe 1.5, right? And then we move farther to the right, maybe here, and then the slope will be again 4, okay, etc., etc. So you see that the slopes are increasing. Okay, so let me write it. Slopes of tangent lines are increasing. Okay, so that'll be one of the ways to tell whether the concave is up or down. What else? Another comment is that any tangent line, let's actually write it too. Let's write it maybe in a different color. So the curve, right? When you look at the curve, and you see all those green tangent lines, so the curve is above any tangent line that I can draw, right? So let's make that comment. So curve above any tangent line. Okay, let's look at another example without calculating anything. We'll just have a graph, so example 2, and again we'll look at we'll look at f of x equals x cubed, and again, right, let's start with the graph. Okay, so cubic function. Okay, so something like this. And again, right, we can look at those tangent lines. Let's have them in green. So maybe tangent line here, you can see it well. Okay, so line tangent to the graph at a particular point. Right, so the slope, again, right, let's think about slope. Maybe I'm just estimating those slopes, right? So maybe m equals, I'm not sure, it looks pretty steep, maybe 5. Right, and then I can move slightly more to the right, and then graph that line over here. So the slope here may be 1. So you see, and at this point, this part of the curve, and you see that the concave is down, right? It's not particularly well drawn. Maybe this would be better, right? And you would see the concave is down, and then the slopes are decreasing. Right, so this part, I'm trying to make it yellow. I'm kind of succeeding, so slopes decreasing. Right, so you see that that's the way we'll be able to tell whether the concave is up or down, right? Whether if the slopes are increasing or decreasing. Okay, and the slopes here will be increasing. Okay, slopes are increasing. So now here concave down. And let's make this, right? So symbol, right? So this is concave down, and here we have concave up, right? So here concave up. Right, so concave up. Okay. Anything else? The slopes are all right. So let's write the definition and let's think about it. So definition. Think about how we can analytically analyze that, right? That concave up or down. So let f be differentiable on certain interval, interval I. The graph is concave up or is concave upward. On that interval. Right, so if f prime, so right, what was f prime? F prime was slope, right? So if f prime is increasing, so think about, right, how can we figure it out whether f prime is increasing or not? Analytically, of course, increasing on that interval, on I. Okay, so how can we tell, right, whether the f prime is increasing or decreasing? Well, we can look at the slopes, right? We can, well, the way we're actually going to be doing it is we'll be looking at the, let's make it, we're looking at the second derivative. So let's look at this f of x equals x squared. Okay, so in the previous section, right, we were looking at f prime. So f prime, and that was 2x. And then we were trying to figure out whether the function is increasing or decreasing, right? So we were looking at plugging in numbers, right, for x, right? Those, I was calling them testing numbers or testing points, to try to figure out whether this is positive or negative. And then we were concluding if this is positive, right, the function will be increasing. Right, so if this was negative, function will be decreasing. So similarly here, right, so we will take, where can I put it? Maybe I can still write it here. So we'll take a second derivative and we will evaluate it. Well, in this case, we won't have to, but in general, yes. Okay, so we won't have to because we just get 2, right? If I take a derivative of 2x, that is 2. Okay, so now you see that this number, right, second derivative is always positive. Right, so our conclusion will be, as I need to write it, conclusion on the next page, concave up. Right, and well, obviously, right, this is a parabola, so yeah, there's a concave up always, right? Yeah, that's kind of how it works, right? We'll take that second derivative and we'll figure out when it's decreasing, increasing, or when it's positive and when it's negative. All right, so let's look at that x cube, right? Let's look at that other example we had, and let's analyze it analytically. So that other example was f of x equals x cubed. Okay, so first derivative was 3 f prime of x is 3x squared. Right, so this function is always increasing because, right, if we plug in numbers for x, right, we always get this positive number except for 0. But we talked about it last time. Anyway, so let's take that second derivative. Oops. So f double prime of x. So that's 6x, right? Okay, so now let's think about it. Let me quickly draw that graph again. Right, if we right, something like this. So now we can take just any number and plug it in for this x, right? So if we're taking numbers, right, that are negative, right, negative numbers, we will be getting. So let's plug a couple numbers in. So f double prime of -1 equals -6. F double prime of -2 -12. Right, so we're getting negative numbers here. Right, so our conclusion will be concave down. Right, so in general, this is not a complicated idea, right? The complicated part is that there's, right, a lot of things, right? Because next section will be graphing using the information that we can gather from those derivatives. Anyway, right, and similarly here, if I take the numbers, the positive numbers, right, so f double prime, let's just do 1, f double prime of 3 we get 18, right? So conclusion here, right, will be concave up. Okay, so one more time, we find the second derivative, right, the way we did here, and then, well, we need to figure out well, this inflection point, or this kind of this critical number, right, of that, where everything changes, or when the concave changes, right, from up to down or from down to up, and then plug in a couple numbers from the left, from the right, and figure out whether that second derivative is going to be positive, like here, or negative, right? And then based on that, on those two pieces of information, we'll figure out whether the graph will be concave down or concave up. Okay, so let's write it down, that conclusion. So conclusion. I'm gonna feel like my writing gets worse. Anyway, so yeah, so let's write if f double prime is greater than 0 for all x's in I, then f is concave up. Okay, so yes, I was using what? Yellow, right? Concave up. I was using yellow for that concave up. Right, so concave up, positive. Okay, and then, well, the other part of that conclusion, right, is that when f double prime is less than 0, double prime less than 0, then f is concave down. And this was red. Okay, concave down. Okay, so minus, and then we have concave down. I was just kind of thinking whether I can fit it here. Okay. Okay, so f double prime, so second derivative is negative, concave down, second derivative positive, concave up. Okay. Yeah, so just like with the previous section, we'll find the one of the steps, right, to finding those intervals where function is concave down or up. We'll be finding those critical points, or in this case it'll be called points of inflection. Okay, so let's write that command to find intervals of concavity. Find critical points. Let's put that. It's not really called critical points. I mean, I'm not really sure. Different textbooks, different authors, right, call it different names. Let's call it critical points. Of f double prime. Right? These are, right, it's not really the same thing, but basically these will be points of inflection. Okay. Yeah, so let me maybe sketch a little graph here, and it's going to illustrate that what we'll be doing. So let's say we have maybe a graph like this. All right, so you see, when I look at this part, right, of the graph, so you see the concave is down, right? And then at some point, the concave is changing to up. Right? And then again, here at some point, the concave is again changing to down. Okay, so this will be that. Let me actually draw it. Right, so the red part, right, concave down, here concave down, and then we have those. Well, before I talk about this, let me add this. Okay, so concave up, obviously the yellow, concave down, the red part, and now we have those points of inflection, right? So these are those points. We have two of them, right? 1 and 2, right? Where the graph changes the concavity, right? So you see, right? It changes from, this is supposed to be an arrow here, changes from down over here, right? Talking about this, down to up, and then from up to down. Okay, points of inflection. Okay, so yeah, let's look at an example. Okay, so let's do an example. Okay, so example 3. So consider so here's the function f of x equals 6 x squared plus 3. Right, so this is our function, and we need to analyze the concavity. Yeah, so basically we need to find the second derivative. I'm not going to do it for you, I'm just gonna give you the answer. Okay, so what I have for the first derivative, yeah, so you should pause the video, right? It's a good exercise to remind yourself how to take a derivative of something like this, right? You could let me just write it here. You could use quotient rule, or you could simply write 6 times x squared plus 3, and that will be to the negative first power, right? So you have that negative that makes that expression under that negative one go down to the denominator, right? So you could, right, take a derivative of that. This would be chain rule, and here you have a quotient rule. Anyway, yeah, so what I got is negative 12x over x squared plus 3, and this is squared. This is 2. Okay, so that's the first derivative. The second derivative, again, right, you should try to do it on your own. Again, quotient rule. And what I have is something like this. So this is after it's been simplified. So I have 36 times x plus 1, x minus 1. Right, so this is the factored form of that, whatever was in the top. And here we have x squared plus 3. And this is to the third power. Okay, so right, just like with that first derivative, right, we need to find those critical numbers, critical points, inflection points, and whatever you want to call it. And yeah, in this case, that will be, let me write that function again. So 36 times x plus 1, x minus 1, over x squared plus 3 to the third power. And we need to make it equal to 0 and solve it, right? So yeah, we can't make that we can't make the denominator equal to 0, right? There's no way. And the top, right, if we look at the top, see that we'll get 0. So the function will be equal to 0 for x equals 1 and x equals negative 1. Okay. Yeah, so these will be our inflection points. So you'll see later that those numbers that you find here, right, those critical numbers that basically means where things change, where things happen. So those two numbers not necessarily will be inflection points. You'll see in a moment or in a couple of minutes what I mean. For now, let's just make an same way as we did it before. So number line. We have negative 1. Let's put that 0 here, 1 here, and let's make those critical numbers, inflection points, blue. And I will pick a couple of those testing numbers. Okay, so maybe negative 2, and we can have 0 as our testing number, right, for this interval, and we can have 2 over here. Okay, so we take those testing numbers and we plug them into the second derivative to figure out what the sign of the derivative is. Okay, so let me do it maybe in a different color so that you can see it better. So let's do f of negative 2, right? F of negative 2. And again, right, I'm not really trying to figure out what exactly this number here is. I'm trying to figure out is that positive or negative. Okay, so I'm taking negative 2 and plugging it right into the function. So for negative 2, right, so I'm here. I'm looking at the top. For negative 2, this will be negative times negative, right? So that'll be positive, and here everything is positive, so that's going to be positive over positive. So that sign here will be positive. Let me actually write it like this. Okay, yellow. So positive, in a little circle, positive over positive. Well, that definitely is positive. Okay, so I'm not worrying about what that number is, but I know it's supposed to be a positive number. But now I want to check, right? So I'll have concave up was yellow, right? So we figure out that this interval will have concave up, right? So it's positive, concave up. And now we'll check. It was kind of right by accident that I made it yellow. Anyway, okay, 0. Right, checking another testing number, testing point. So for 0, okay, so I'm plugging 0 to the top. 0, I get negative on the top, positive on the bottom. Okay, so I get negative over positive. So negative over positive equals negative. Okay, so I think it was red, no? I don't remember. Yeah, concave down was red. Right, so we're here, negative, negative, negative. This whole interval is negative, so that means concave down. And then we're plugging in that last number, f of 2. And again, right, so I go to the top, right, numerator, it looks like positive, so positive over positive, positive here is definitely positive. Okay, so again, this is positive. All this whole interval is positive, so concave up. Okay. So now you see that right, so the graph changes its shape from concave up to concave down. So here that negative one will be point of inflection, and then 1 is going to be also point of inflection. The function is defined for both of those points. So those definitely will be points of inflection. I'll show you in a moment the situation when that's not the case. But yeah, so let's graph that function and see what's going on. Okay, so it looks... Okay, so this is 1, or this is negative 1 actually, right? This is 1. And the graph will look... I'll try to make it in such a way that actually at those, right, positive 1, negative 1, the graph actually does... I didn't manage here. Anyway, right, so those points of inflection where the graph changes, right? So concave up. Looking at this part, right? So concave up, right? Changes to concave down, right? And then back to concave up, right? So we have those 2 points of inflection. Let me try to make that a little better. I hope I can. Yeah, maybe something like this. I'm not sure. Maybe I should have drawn the graph first and then... Okay, how did it go? Yellow was up, concave up. Alright, so let's make this part up. Let me redo this graph. Maybe I'll graph it first and then I'll mark those points of inflection. I think that's a better way to do that. Okay. So here's the x-axis. And yeah, so the points where the graph changes, right? Changes from concave up to concave down. It's going to be somewhere here, right? The same thing here. Okay, so this is the negative one. This is the positive one here. And still, the picture is not very good. Anyway, it is what it is. I'm not going to redraw it the third time. I hope you understand what's happening. Concave up over there, concave down. So arrows are pointing down, right? Also do this. Okay. So let's write a couple additional comments. Okay, so let's write a definition of inflection point. Okay, so I point C, f of C, is a point of inflection. As I said, my writing is getting worse. Point of inflection. If the concavity as you can see, I'm struggling. If the concavity changes. at that point. Okay, so yeah, so that's the definition basically. And let's make another additional comment here. So that's it's similar with those critical points. So let's just write at inflection points. They have to be right in domain. We'll have that f, and that second derivative of x equals 0, or that second derivative at that point doesn't exist. Okay, I'm going to write equals doesn't not exist. Okay, so just like with that first derivative, and I'm gonna give you an example. So